I'm Michaël Marcozzi. I'm a tenured researcher at the KLEE Institute of Université Paris-Saclay in France. And I'm very, very happy to be back here at Imperial, where I've been a postdoc a few years ago with Christian and Ali. And today I will give you a very short introduction to our ongoing work in Paris about building a tight integration between symbolic execution and fuzzing. Oh gosh. So yeah, what is fuzzing? So fuzzing is basically automatic test input generation, and it exists in different flavors. So the first one is black box fuzzing, where you just consider the program that you are testing as a black box, and you try basically to generate inputs for it, test inputs for it randomly. And you usually can use some kind of a specification of the program that you are testing and of the input format that it is using. Then you have gray box fuzzing, where you put a bit more intelligence about the structure of the code that you are testing in the test generation process. And basically what you do is that every time you generate a test input randomly, you run it on your program and you monitor the coverage that you get, the code coverage. And if you see that this test input increases the coverage compared to the previous test inputs that you have tried before, you keep this new test input that brings new coverage, and you try to mutate it randomly in the hope of getting even more coverage. And for fuzzing guys, actually, symbolic execution is just nothing else than the third form of fuzzing, which is white box fuzzing. So the idea here is that you have a full white box access to the program that you are testing, so that if you want to test a specific behavior, you are free to gather the exact constraints on the test inputs that will trigger this behavior, and then try to get a correct solution of these constraints using a dedicated solver. And
is that dynamic symbolic execution?
Yeah, I would say yeah, dynamic symbolic execution, but yeah, I think you static, you can also build a test input. It's more like test input generation. I don't know if we can accept questions or okay. Sorry. Yeah. Okay, and so guys, as we didn't take long for guys to basically realize that gray box fuzzing and symbolic execution were in some way complementary, because yeah, if you use gray box fuzzing, you don't have these common issues that you can get with symbolic execution, like the path explosion problem, or the fact that you end up with constraints that just blow off your solver. But in the other end, it will really struggle to cover these parts of the code that are protected by a condition that is typically triggered by only a really tiny fraction of the testing of the program inputs. And this can actually quite easily be done, usually without really big problem, by symbolic execution. And so several recent tools have aimed at building a hybrid fuzzing approach, which try to get basically the best of both worlds. And what we are trying to do in this work is trying to build yet another hybrid fuzzing tool, which we hope will be a bit better or even more really better than the others. And basically our goal is trying to tick all the boxes of what we consider to be a really tight integration between symbolic execution and fuzzing. And basically our two main principles are, first, to rely on gray box fuzzing to explore the path space. But in the case where we want to target paths that need to go to pass a condition that is only triggered by a tiny fraction of inputs, basically we look at the prefix constraint that reach this condition, and we express it in a simplified form called easy enumerable. And in this simplified form, actually, the gray box fuzzer itself can be used as a constraint solver for solving such simplified constraint, and so can quickly generate solution to the constraint and test inputs that will cover the path. And so to conclude, basically, we got good, really preliminary results against the state-of-the-art gray box fuzzing and symbolic execution tool on rather small programs. And our ongoing work is first to extend our simplified constraint language, and then to evaluate our approach at scale versus state-of-the-art hybrid fuzzing tool. So that's it. Thank you, and let's discuss it around the poster. Cheers.